Hello students, let us review the 2023 A-Level Paper 1. Thanks to the students for providing the sample scripts. Okay, so we'll take a look at question 1. For question 1, you have neodymium, Nd, and then you have promethium. They are both lanthanoids. Okay, so lanthanoids, they are what we call the further transition elements. You might want to take a look at the data booklet to see where they belong to. Okay, so you can find them over here. You can neodymium is Nd, so it's element 60, so it's over here. Yeah, and then promethium 61. Okay, so that means that they have 60 and 61 protons respectively. Okay, so I might just want to put it here, 60 and 61, just to remind myself that that's the number of protons they have. So we have an isotope of neodymium plus 2 plus, and another isotope of promethium 3 plus. Both have 145 nucleons. So which row of the table is correct? Okay, so you just have to examine all of them, but maybe I will put it a little simply. So I just put it at the side. So I have Nd 2 plus. Okay, so in this case I have Nd 60, and then I have 145. Okay, then I will have Pm 3 plus. Again, this is 60. Oh, sorry, this is 61. Okay, and then 145. Okay, then number of protons. Okay, so that will be 60 and 61. Then the number of electrons. Okay, if we want, that will be 58. Okay, remaining, so that will be 58 as well. Okay, the number of neutrons. Okay, so we'll just do a simple subtraction. 145 minus 60, that's 85. Okay, so that's 85, and then we have 145 minus 61, that's 84. All right. Okay, so you just have to examine all the options. Ion with a larger number of neutrons, that will be neodymium. Okay, so yeah, so the students take these two options. Okay, A and B, and then ions with larger number of electrons. Okay, so both the same. Okay, so we have already worked them out. So over here, they are the same. Okay, so student take this option. So that will be B. Okay, so question 1 will be relatively straightforward. Next, we'll take a look at question 2. So we have electronegativity values of 3 unidentified elements, X, Y, Z. You are given the values. So it might be easier if I just write them out over here, so that it's easier for me to refer to. So we have X, Y, Z. X is 1.2, Y is 0.9, Z is 1.8. And then I am also given oxygen and chlorine. So oxygen is 3.5. Chlorine is 3.0. Okay, and then the question is, which pair does the first compound have greater ionic character as compared to the second compound? Yeah, so of course the students know what to look out for. Yeah, so the greater the electronegativity difference, the greater the ionic character. Yeah, so I think what he or she did was just to calculate the electronegativity difference. It's probably not written out here. Yeah, but the easiest way for you to do is to check through everything. Yeah, because sometimes for MCQ, especially for a relatively simple question like this, it does help a lot if you can check through everything and see, ensure that you don't miss out any possible answers. Okay, so we'll just take the difference between X and Cl. So X and Cl, that will be 1.8. Okay, so 1.8, and then Y and O, that will be 2.6. Okay, yeah, so in this case the second one is bigger than the first, so I'm not going to choose option A. Okay, then for XO, that will be 2.3. Y2O, that will be 2.6 as well. So again, the first one is lesser than the second one, so nope, so I'm going to cross it out. And then for YCl, that will be 3.0 minus 0.9, that will be 2.1. Yeah, and then ZO2, so that will be 3.5 minus 1.8, so that will be 1.7. Okay, so the first one is bigger than the second one, So that means that the first compound has a greater ionic character, so I'll pick option C. Yeah, but in order to ensure that I'm on the right track, let's take a look at D. So ZCl, that will be 1.2, XCl2, that will be 1.8. So the second one is bigger, so I'm going to cross this out. Okay, so in this case the option is C. Right, going to move on to question 3. The table below, okay, the table shows boiling points of 2 organic compounds. Okay, then which statement explain the relative boiling points of these two? Okay, this tends to be a question that is asked in free response sometimes. So normally over here you observe that the boiling point of CH3Br or bromethane is higher than that of chloromethane. It may be a little bit shocking to some of us when we first study chemical bonding, because the CBr bond is less polar as compared to CCl, so you expect the permanent dipole interaction of chloromethane to be stronger than that between bromomethane. Yeah, however, it's shown to be not the case, because in this case the boiling point clearly differs by quite a bit, and it showcases that in our case here, bromomethane being less polar has a higher boiling point. Then what could be the reason? Yeah, so the main reason here is of course due to the strength of the dispersion forces, or otherwise we call it the instantaneous dipole-induced dipole interaction, and that has got to do with the size and therefore the polarizability of the electron clouds. So I'm expecting the bromine, okay, being a bigger atom as compared to chlorine. In this case, for bromomethane, the electron cloud is larger and therefore more polarizable than that of chloromethane, and that will lead to a stronger dispersion forces between bromomethane molecules as compared to that between chloromethane molecules. Okay, yeah, so that would be the perfect explanation if you know where I'm coming from for a free response question. So in this case, the dispersion forces will take precedence as compared to the permanent dipole interaction. But if you look at MCQ, you read through all the options, it seems that none of the option works. Yeah, so if you read through, which statement explains the relative boiling points of chloromethane and bromethane? Option A, Cl is more electronegative than bromine. Yeah, I'll definitely cross this out. Yeah, remember this, because if that is the case, if PD takes precedence, I'm going to expect chloromethane to have a higher boiling point, but that's not the case, so I'm going to cross it out. B, there are hydrogen bonds between blah blah and not between blah blah. This is nonsense, because hydrogen bonds, remember, we are only looking at protonic hydrogens, and there is H bonded to F or N. Not the case over here, so I'm going to cross this out. C, bromine atom contain more electrons than chlorine atom. I will put a question mark here, because obviously you're not going to write this for structure and free response questions, right? Yeah, but it does showcase that it has a larger electron cloud indirectly. Okay, so I'm going to put a question mark. D, the covalent bonds are stronger. Definitely no. Okay, so in fact the CCl bond is stronger than that as compared to the CBr bond. Yeah, you can easily check the data booklet. If I can, I'll just show you from the data booklet. If you want, you can, but I don't encourage you to check, because there isn't a need to. But if you want to, just for the fun of it, just check. CCl is 340, CBr is 280, so it's stronger. Yeah, so it's wrong as well. So again, we are left with no choice. Pick the best option, right? So C will be the best option, but don't use option C as your answer to structure and free response questions. Okay, yep. Question 4. Okay, which species contains a total of 8 shared electrons? Okay, so they are talking about shared electrons. Again, do we have to run through all the category? I guess we have to, unless you are very strong in your concept. Then you do not have to. Okay, so okay, students choose to draw dot and cross for some and structure formula for some, but it doesn't really matter. It's up to your preference. Okay, so I think for me, just drawing the molecular formula will help me. Okay, so this is H like this, and then the whole thing is a plus charge. Okay, the number of shared electrons in this case 2, 4, 6, 8. So because there are 8 single bonds, yeah. So ammonium, yes. CO2 student drew it here, so I'm not going to redraw. So 4 times 2, so 8 in total. So CO2 as well. Methanol student drew it here. There's a carbon here, in case you might have forgotten about it. So 1 double bond, 2 single bonds. So 2 times 2, 4. 4 plus 2 times 2, that will be 8. So again, methanol works. Okay, so D. Right, so question 4 is quite straightforward in this case. Question 5. How many of the molecules listed are polar? Okay, so keyword is, let me highlight, polar. Alright, so let's look at the polar bonds. Okay, whether there's a net dipole. Okay, so 1,1-difluoroethene. Okay, so student drew it out here. Okay, am I expecting a net dipole? Yes, probably in this direction. Okay, cis isomer. Okay, so student drew it here, so probably in this direction. Okay, so there's a net dipole. So the trans one is the one where it will get cancelled out. Okay, then what about tetrafluoroethene? How does tetrafluoroethene work? So it's basically everything replaced by fluorine. Okay, will there be a net dipole? No, because if you try to resolve the vectors, okay, over here will point in this direction, over here will point in this direction, and because we are looking at the same elements being bonded to carbon, that is fluorine, so these two will cancel out. So in the end, no net dipole. So no net dipole, no net dipole. So a total of 2 molecules. So we are looking at option B. Okay, yep. Next, question 6. Use of the data booklet is relevant to this question. P is the number of period 3 elements which have only 1 orbital in the outermost shell, which contain just 1 electron. Okay, so it's period 3, 1 orbital, okay, 1 electrons. Q is the number of period 3 elements which have only 1 orbital in the outermost shell, which contains a pair of electrons. So which row is correct? Alright, so what is the simplest way to tackle this question? Okay, is to look at the periodic table, of course. Go all the way to the end. Okay, over here. Okay, we look at period 3. So from sodium all the way until argon. Let us try to write out the electronic configuration. If you wish to, you can. If not, if you can count in your head, you can do so. But for illustrative purposes, I'm just going to write out everything. Okay, so we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, so I'm just going to write some short form. I know some of you might not like it because it doesn't showcase reality, but it's okay. I'm going to write short form here. So 3s, I have 1. Okay, magnesium is 3s2, aluminium is 3s2, 3p1. Okay, and then so all this will be filled. Probably I'm just going to write quickly. Okay, I'm going to continue. So this will be like this, and then after that like this. Okay, then like this, and then all filled. Okay, then we can do a quick count. So that would be one of the most straightforward way in doing this question. Okay, 1 orbital in the outermost shell which contains only 1 electrons. Okay, so how many are there? Okay, so this is 1. Okay, this is 2. Okay, and 3. Am I right to say that? So 1, 2, 3. Okay, so in this case, I'm going to circle either option C or D. I'm going to use another colored ink, in this case pink. Okay, 1 orbital which contains a pair of electrons. So that will be 1. Okay, what else? Okay, 2, 3, and oh, I missed out one. 4. So 4 in total. Okay, yep. So I'm going to circle this. So the option will be D. The answer will be D. Right. We'll move on to question 7. Which statements about the behavior of group 2 elements from magnesium to barium are correct? Okay, so as you go from magnesium to barium, what are you expecting? The elements become stronger reducing agents. Okay, so that means that they have a greater tendency to lose their valence electrons, and you know that that is true because as the number of electrons, or rather the number of principal quantum shell increase, the outermost electrons are less tightly held by the nucleus, despite an increase in nuclear charge. Yeah, because of the distance now play one of the major role, or one of the more important role in deciding whether they are more easily lost or less easily lost. Yeah, so because of that, they can more easily lose the valence electrons. That makes them better reducing agents. Okay, so 1 is correct. 2, the thermal stability of the metal carbonate increases. Is that true? That is true, because remember, for group 2 cations, as you go down to a group, the charges remain as +2. Yep, but the cationic size actually increases. Yeah, so when the cationic size increases, that means that the charge density decreases. Yeah, so that has got to do with how readily, okay, or how strongly the cation can polarize the anionic electron cloud. In this case, how strongly they can polarize the carbonate electron cloud. Yeah, and because the charge density decreases, yeah, polarizing power actually decreases as well. So they are not able to polarize the carbonate electron cloud as strongly as those higher up in the groups. So that means that magnesium carbonate is likely to decompose at a lower temperature as compared to barium carbonate. Yeah, so because of that, I expect the thermal stability to increase down group 2. What about part 3, or option 3? Charge density increases. We just said that the charge density decreases. Okay, so this is incorrect. So we're only looking at option A to be the correct answer. Alright, so we'll move on to question 8. Okay, a sample of silicon contains 3 naturally occurring isotopes. Okay, so we have the 3 over there. So the sample is made up of 92.23% of silicon 28, and the relative atomic mass of silicon is 28.10. Then question asks, what is the percentage of the isotope 29 silicon in the sample? Okay, yeah, so students have already worked out the math over here. Okay, so if we wish to, we can check it out. Okay, so first of all, we know that silicon 28 is 0.9223. Okay, then if you let silicon 29 be x'd, silicon 30 will be 0.0777 minus x. Okay, does that make sense? Okay, so from here we can formulate the equation. Okay, so I'll just find some space to write. Maybe I'll just write in the space here. So we have 0.9223 0.9223 times 28 k plus x, so that would be 29x. Okay, then plus 0.077 minus x okay, minus x multiplied by 30. Okay, and then I will equate it to 28.10. 28.10. Okay, then right now I'm just going to attempt to punch my calculator. So 0.9223 times 28, okay, plus, wait, sorry, 0.9223 times 28, okay, and then I'll bring it to the other side. Okay, then I will get 2.2756, so then I will have 29. Okay, so here I'll get minus x because it's 29x minus 30x, so I'm going to get minus x. Okay, so this will be equals to, okay, then I'm going to bring, I'm going to multiply 0.0777 times 30. Okay, I bring it to, oh, I forgot to write the number down. Okay, so I'm going to use the eraser. Okay, so sorry, minus x, and then this will be x plus 2.331. So this is equals to 2.2756. Forgot to write this down earlier on. Okay, and then I'm gonna shift the thing over, so I'm gonna minus 2.2756. So I'm going to get x to be equals to 0.0554. Okay, so that will be 5.54%. So that will be option C. Okay, so which is correct. Okay, the correct option chosen by the students. Okay, next, question 9. We have 50 cubic centimeters of 2 moles per dm³ H2SO4. You add it to 100 cubic centimeters of 1 mole per dm³ of sodium hydroxide in an insulated vessel. Both solutions are at a temperature of 20 degrees Celsius before mixing. Okay, and then on mixing, the temperature rises and the highest temperature recorded was 29.0. Okay, students already wrote a delta T to be 9 degrees Celsius. Assume no energy loss to the surrounding. Assume the density to be 1 gram per cubic centimeter. Specific heat 4.18 joules per gram per Kelvin. What is the value of the enthalpy change of neutralization as determined by this particular experiment? Okay, so I have 50 cubic centimeters here, 100 cubic centimeters over here. Okay, so I have Q is equals to MC delta T. The M is 150. Specific heat 4.18. Temperature change, that will be 9. Okay, I will punch the calculator, but just believe the student's value is correct, so it's 5643 joules. I mean, I can verify it later. Okay, is there a limiting reagent here? Okay, so let's try to calculate. Shouldn't be. So what is the number of moles of H2O form? So that will be 0.1, right? I think the students put here 0.1. So the number of moles of water form is 0.1. Yeah. So in this case, what are we going to do over here? Okay, right. So enthalpy change of neutralization. Enthalpy change of neutralization is equals to, okay, I'll just use the calculator to verify the values in case anything goes wrong. 150 times 4.18 times 9. Okay, so that will be divided by 0.1, right? Okay, so because temperature increases, so we take negative 5643 divided by 0.1, so we get minus 56,430, so that will be about minus 56.4 kilojoules per mole. Okay, so in this case, we'll choose option A as the answer. Yeah, and if it's between a strong acid and a strong base, you're expecting the answer to be close to minus 58 kilojoules per mole. So remember that. Okay, so cesium chloride, or rather calcium chloride, does not exist as a stable compound, but its lattice energy can be estimated. What is the predicted order of increasing magnitude of lattice energy? Okay, CaCl, CaCl2, MgCl2. Okay, so again, lattice energy, students wrote it out, is directly proportional to the products of the charges, inversely proportional to the sum of the ionic radii. Okay, minus. Okay, so if you want, you can check. If not, it doesn't really matter. Okay, I think we don't have to check, because Mg magnesium lies above calcium. Yeah, so the cationic radius will definitely be, or rather, cationic radius of Mg2 plus will definitely be smaller than that of calcium 2 plus. Yeah, so because of that, we can straight away conclude that the one with the most exothermic lattice energy will be MgCl2. Okay, so because of that, there's only one option we're going to look at. That's option A. Yeah. What about between calcium chloride, CaCl, and CaCl2? Well, that is obvious, because for CaCl, we are looking at the product of the charges to be +1 times minus 1. Or rather, +1 times -1, which is essentially magnitude of 1. But CaCl2, we are looking at magnitude of 2. So definitely, if you compare, this CaCl2 will be more exothermic as compared to CaCl. Yeah, and because calcium 2 plus is bigger than Mg2 plus, I expect CaCl2 lattice energy to be smaller than that of MgCl2, and therefore I'm only going to select option A as the option.